tickled and honored to be here today. It's terrific to be back in O'Dowd. I'm delighted that Dittmer has invited me, and what I'd like to talk about is probably not what I'm going to talk about. Before I started, I noticed that somebody, hold on, stay right there. Somebody had written on the chalkboard, or the pseudo chalkboard, math is awesome. One of the things that cheeses me off, upsets me deeply, and starts me sort of wiggling a bit, is what I hear in hallways. People say math sucks. And people say, hey, I don't like it, and it's bad news. And I hate math. And I don't like numbers. If your idea of mathematics is math is all about numbers, then it's sort of like your idea of Shakespeare. Shakespeare is all about words. If your idea is the Mona Lisa is all about paint, or poetry is all about putting letters in a row, then yep, mathematics is all about numbers. But to me, the Mona Lisa, Picasso, Rodin, it's not about paint, it's about beauty. That quality art. You look at it and you say, wow, that's cool. Poetry, Shakespeare, Macbeth, tomorrow and tomorrow and tomorrow creeps in this petty pace from day to day, and all our yesterdays have lighted fools. Out, out, brief candle. Life's but a passing shadow. A poor player who struts and frets his hour upon the stage and then is heard no more. It is a tale. It is a tale told by an idiot, full of sound and fury signifying, well, this is just a collection of words strung together. In the same way, I could start saying, oh, 1, 2, 3, 4, dot, dot, dot. And pretty soon everybody would fall asleep. I had a professor did that once. He started talking, and no, mathematics has, and implicit in mathematics, is a beauty and a logic that is as moving and as eye-popping as is Shakespeare or any great painting. One of the problems that we have is that all of us think that we're really logical. But when you really put it to the test, logic is based almost entirely in mathematics. A lot of people, they hear math, they want to scoot away from it. Don't be that way. When you hear somebody smearing math, realize that they're saying more about themselves than they are about a field. They're saying more about what they're interested in than what you should justifiably be interested in. What happened to lights? Since I can't see anymore, one of the things I'm interested in is a branch of math. Somebody turn lights back on. A branch of mathematics called topology. Topology is a part of mathematics which deals with surfaces, the property of surfaces, and the properties of things like strings and knots and what does it mean to have a connection from over here to over here? Well, you say mathematics is all about numbers, but these guys are holding up a long, flexible rectangle. Stand up. So I'll grab this in. Here's a rectangle. You've all seen packing material like this. And I assume all of you realize that, oh, how many edges? 4 edges. Top, bottom, east, and west. Yeah? How many sides? How many sides? What? 4 sides? I see a front side, and I'm touching the back side. 2 sides. 2 sides, 4 edges. How many corners? 4. Okay. So, as all of you know, we can connect this easily into a hoop. And this is part of the cylinder. Yep. Nothing up my sleeve, don't have sleeves. Equally well, they can connect this into a Mobius loop. Go ahead. And what did they do to make it into a Mobius loop? Come. How do you make a Mobius loop, guys? Give it a half twist. So, okay, they're holding up a Mobius loop and showing it to everybody. It's got 1/2 twist. Okay, go back to 4th grade when you first started playing with Mobius loops. How many sides does it have? What? 1 side. They've changed a 2-sided thing into a 1-sided thing by just scotch taping it together and giving it a half twist. Giving it a half twist first, and then scotch taping it together. So, okay, I assume, how many people, I should have said how many people don't know what a Mobius loop is, but I'm not going to insult you. So instead, you don't know what a Mobius loop is. Nudge the person next to you and say, tell me what a Mobius loop is. And the person next to you is going to say, oh, a Mobius loop is when you take a piece of paper and instead of connecting it like this, you give it a half twist like this. And then the person next to you is going to say, oh, there if you tape it together like that, it has amazing properties that instead of having 2 sides, 1, 2, suddenly it has only 1 side. And this is truly bizarre. Wow. That with a half twist, you can show that this piece of paper, or this, prove that it has only 1 side. Quick, 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 up, fast, fast, fast. Right there, draw the letter A right there, big. On 1 side. Come on, fast. Don't have time to wait. Start with your hand there. Trace around. Keep going, keep going. And he got to the other side of the, step back so other people can see. He got to the other side of the A. So I can write a B over here. So the red B is on the same side as the green A. Check this out. That thing there has 1 side. This hand right here, right, goes from here around like this. Keep going. And shows up touching that B. What this is saying to us is the thing that these guys made has 1 side. A piece of paper with 1 side, and you can make it yourself. You know, just tear up your homework tonight into little strips, give them a half twist, and scotch tape them together. Don't erase your hand. Now, there are even more wonderful properties of the Mobius loop that you're on stage right. Stage left is always a better place to show. So, one of the weird things about a Mobius loop is it's got only 1 edge. Remember we started out, it had 4 edges? Well, when you take a piece of paper and connect it to another piece of paper, here's 4 edges and here's sort of 4 edges. I connect them together like that. I have to lose this edge and I got to lose that edge. So I subtract 2 edges. So that started out with 4 edges, but by giving it a half twist, it ended up with only, quick. Start here and go around this side so people can see that you're doing it legally. Start over here and show everyone that it has 1 edge. By starting here and draw along there, she's tracing out this edge. Keep going. Stay along the edge, same side, no for crossing edges. Keep going. Well, sort of an edge, right? The cool thing is, that piece of paper's got 1 edge. It started out with 4 edges. We tied it together and got rid of 2 edges. But now it's only got 1 because we put a twist in it. Weird stuff, and the kind of stuff you, thank you very much. So, as many, if not all of you know, this Mobius loop is highly popularized now, and you can buy or knit your own, and they're often called infinity scarves. And infinity scarf, of course, your arms are getting tired too bad. A Mobius loop, also called an infinity scarf, has a half twist built into it. So the red edge over here is the same as this red edge over here. Hot damn! This is saying that, check this out. Look, this edge along here, I can follow it around, I come back, that's this edge. Look. Yeah, keep going. Does it come back? Oh, wait. We have an authority. Does it come back? Yeah. Now, what's stunning about this is, just like that Mobius loop, this has how many sides? 1. It's a 1-sided Mobius loop with 1 edge. There are truly wonderful things that you can do with the Mobius loop. And a pair of scissors. Happily, I didn't bring a pair of scissors with me, so or maybe I did. Sure, come on. Yeah! You know how to use these? Be very careful. They're dangerous. Start right here and cut. This way. Keep 2 inches along here. Yep. And help her. She's cutting this sort of down the middle, right? Those of you who know this are already rolling your eyes and said, I did this in 5th grade. Those who don't know it are going to say, wait a second, there's clearly nothing up her sleeves, but something's going on. Hey. Keep going. Don't stop now. Fuck. Not too fast. You're getting way ahead of everything. Will it keep going forever? Maybe. she's almost there. Look at this. One more snip. Ah. Grab an end of this. Notice something that's transcendently fantastic. Check this out. She never took, your name is? Olivia, never took the scissors away from this, but after cutting it, there's now 2 loops. And they're interconnected. One of the niftiest things about topology is, so far we've sort of mentioned the number 4, the number 2, and the number 1, and it's one side in all of this. But we really haven't been talking about math or algebra or anything, but something weird is going on here. By cutting this into 2 pieces, you ended up with something that's linked like this, and there's a whole branch of mathematics developed by this guy, invented by the great mathematician Euler, further developed by Gauss, by Banach, by Tarski. I can't even mention the man's name, Gödel, without just getting a shiver up my spine. The unprovability theorem. I won't talk about any of those wonderful things. I will mention, however, that a whole branch of mathematics is called knot theory. The theory of knots. How do is this a knot? Is this a knot? Is this a knot? How come I get tangles in my hair? Why? I used to. This is probably your reading. Thank you. You can sit down at the edge of me over there. Thank you very, very much. So, how much time do I have?
Get out in.
No. How many minutes? 30 minutes, half an hour. Okay. So, I'll start talking. I'll start doing my talk in a few minutes. Suppose, for a minute, I made a Mobius loop like this. Right? Remember, just like the ones they made. And I went home and got out my 500 horsepower Singer sewing machine. And I say, what would happen if I took, is there a Mobius loop floating around here?
Where?
No, hang on to this. There's a Mobius loop, here's another one. Right? So here's 2 Mobius loops. Hand knit by my hands. So this has how many edges? 1. How many edges does this one have? 1? Yeah, well, he doesn't believe me. Didn't believe me, right? Right? What? No, I don't care about being awesome. I want proof. The cool thing about math is not awesomeness. The cool thing about math is you can prove it by just saying, hey, I'll start here. That's the same length, 1 edge. This has 1 edge. Well, you know that if you connect 2 pieces of paper together, this one with 4 edges, this one with 4 edges, I connect them together to show the guy on stage half an hour ago said, you'll lose at least 2 edges, right? Well, what happens if I take this thing that has 1 edge and this thing that has 1 edge, get out my sewing machine, and I sew them together like this? Make sense? First principles, how many edges should I end up with? 1? Wait. How many do I start with? How many edges here? 1. So I start with a total of 2 edges. I sew them together. How many edges should I end up with? None. Can you have something that has no edges? Yeah, name something that has no edges. A what? A sphere. A sphere, the globe has no edges. One of the cool things about an Einstein universe, or an Einstein universe, is that you have a universe that's finite but unbounded. A sphere is finite, has a certain area, but has no boundary. There's no edge to it. In the same way, you can connect things together and get something that has no edges. Well, I was sitting around and I discovered a wonderful device for my sewing machine called a zipper foot. And I put a zipper foot on the machine and put a zipper on, and I made 2 Mobius loops. Mind you, this is a Mobius loop. Not as pretty as that one, but it's a Mobius loop. You can see there's a half twist to it. This also is a Mobius loop with a half twist. 2 Mobius loops. And I inset a zipper. So put a zipper in there. I'll zip them together and I should lose an edge. Right? In fact, I should lose 2 edges. Well, after doing this quaint experiment, I get something like this. It's got a hole in it, which is a useful thing to note, that each of these have exactly 1 hole, right? That has a hole and this has a hole. So I expect sewing them together, I'll keep a hole. But curiously, something that you can't see, but my good friend Felix Klein is aware of, that the zipper necessarily has to stop right here. It can't go through itself. There's a problem that the zip, in order to finish connecting the edges together, they have to intersect one another. In 1882, Felix Klein realized that if you sew together 2 Mobius loops, you get a weird shape, which is now called the Klein model. You get a weird shape which cannot exist in our universe. Normally, we live in a universe that has 3 dimensions, 3 space dimensions. Forward and backward, left and right, up and down. So our normal 3 space has, up, down, forward and back, left and right. We also have a cheesy 4th dimension, not a very nice 4th dimension, called time. Physicists love time, but mathematicians kind of ignore it. Because, unfortunately, unlike a space dimension where you can go, you go walk forward and walk backwards, time won't let you do it. So I'm going to ignore time. It's not very interesting. But normally, a Mobius loop, the remnants of this Mobius loop, if I looked at just a real tiny neighborhood, a real little place on it, right here, that neighborhood right there, it would be what mathematicians love to say, locally Euclidean, which means that Pythagoras would be really happy there. Of course, Pythagoras loves it when right triangles are the sum of the squares of the legs of a right triangle equals the square of the hypotenuse. If that's true, everywhere on the surface, in other words, if I can draw a little right triangle there, and that area plus this area equals that area, if that's true, it's locally Euclidean. Turns out that this stage that I'm walking on, under my foot, it's locally Euclidean. Up there, that's locally Euclidean. I can say, this piece of paper, I'll try it out. Check that out. A, B, A squared plus B squared equals C squared. Not bad. There's a problem though. This may obey Euclid's law, and Pythagoras might be happy in the middle of it. But there's a place on this piece of paper where Pythagoras would be really frustrated, namely the edge. The points along the edge of a piece of paper, you can't draw a right triangle without part of the triangle falling off the edge of the piece of paper. In other words, a piece of paper, this stage, and a lot of things that we deal with every day, are Euclidean near the middle, but not at the edge. Your math teachers will tell you about the wonders of bounded and unbounded spaces, of the difference between a limit and, ask them. But as far as I'm concerned, the curious thing about edges is they cause trouble. So it's nice for me to think that here's something, when I connected those two Mobius loops together, here's something that has no edge. It's not just locally Euclidean, it's everywhere Euclidean. A sphere is, on a large scale, non-Euclidean. Euclid's properties don't apply. A squared plus b squared doesn't equal c squared. Triangles don't have 180 degrees if you add up all their angles on a big sphere. But if you look small enough on the Earth, it does work. Felix Klein looked at this, started thinking about it, 1882, 1883. Who knows German? Anyone speak German? Good. Ha! He wrote a paper called Nicht Euclideische Geometry, which I'll translate for you. Translated says nighttime Euclidean geometry. He was teaching night school. And he said, just like with a Mobius loop, you can take a tube and make it into a hoop, or you can intersect it like this. And in doing a self-intersection like this, Felix Klein said, if I sew these two Mobius loops together, I get something that ultimately would be called the Klein model, which cannot exist in 3 space. Oh, going back to this Mobius loop. Mobius loop everywhere is locally 2-dimensional. In other words, I can squash it down and it'll fit on a table. However, it needs 3 dimensions to exist, right? When you're holding it up, you had to hold it up. I squash this down flat, it's no longer a Mobius loop. So here's something that like a sphere, is locally 2-dimensional. It's flat, but the whole sphere requires 3 space to exist in. A Mobius loop is locally 2D and requires 3 space. Klein's model is locally 2-dimensional, but in order to properly exist, it requires 4 space. It requires height, width, depth, and something else that we can't imagine. Our brains won't wrap around a 4th spatial dimension. And so, unfortunately, I can't show a real Klein model here. But the closest I can do is to show the shadow of a Klein model. This is a model, a glass model that I made of a Klein model, which, if you were an ant, here's an ordinary bottle. It's got 2 sides. It's got an outside that has a label saying renewable distilled water on it. It's got an inside, my finger's touching it right now, right? I'm touching the inside. Separating the outside surface from the inside surface is the lip of the bottle, right? People probably don't trust me on this, but if you look right there, you see a little circle there? It's called the lip of the end, or the edge of the bottle. If I make this bottle arbitrarily thin, suppose instead of being made out of 1 millimeter or 2 millimeter thick plastic, I make this plastic be a zillionth of an inch thick. So thin that if I put my finger around here, I slice my finger, right? This lip then becomes an edge. Here's an edge. So I have an edge separating the outside surface from the inside. If I made it out of glass, right now I'd be bleeding. So the idea here is, what I call an open bottle like this has 2 sides, an outside and an inside. The cool thing about a Klein bottle is it has I make this out of arbitrarily thin glass, and it's pretty thin glass right now, it's still a smooth curve to go from the outside over to the inside. Yes, no? Notice that even if I make this really, really thin glass, I don't cut myself as I move around like this. In fact, a real Klein bottle, can be proven mathematically, but you can just look at it and say, it has no sharp edges, until he drops it. And so the idea here is a bottle, not only is it have no sharp edges, but it has one side. An ant walking around here, if I started an ant walking along here, it could clearly walk all the way around here without reaching an edge. It could walk up this tube around and cover the entire surface without ever reaching an edge. So, unlike a sphere, where an ant can walk around the outside but can't get to the inside, here an ant can cover both sides of the bottle without ever really crossing an edge. This is an unbounded, one-sided bottle. It's one-sided in the same way that you proved that this is one-sided. In fact, it has to be one-sided because it's made out of a pair of Mobius loops. How do I know that? Well, suppose I take a scissors and do the same experiment. I'm going to take a scissors and cut this. I'll cut this in half. So, happily I don't have a sharp scissors like that, but I do have a diamond saw. So I took a ordinary Klein bottle like this and a diamond saw to show that I got to pass this back. Kindly don't drop it, but feel free to cut yourself on the edge, and you'll notice that if you start with your finger here and go along like this, that this, in fact, has only one edge. So this has one edge, and if I start here, I can trace this out and show that it has one side. One side and one edge. Cool stuff. In other words, a Klein bottle necessarily has, grab one, not three. A Klein bottle necessarily, A Klein bottle necessarily has, this of course is half a Klein bottle. And as half a Klein bottle, this is a Mobius loop. So, people at home will realize that this, I can start along here and demonstrate with my finger that this has only one edge and it has only one side. Here, throw that around. Again, don't drop these. They're sort of hard to make. It's the nature of a Klein bottle not only to have one edge, no boundaries, but how much time do I have? 20 minutes. Oh, far out. I'll start. Maybe I should start now. Mathematicians know and love Klein bottles as a shape whose inside is the same as its outside. A surprisingly difficult and challenging thing to prove in mathematics. And the best parts of mathematics are proofs. One of the cool things about the quadratic equation is that you can prove it, you can derive it. Well, one of the hard things to do in math that's been done, but it's hard to do, is to show that a bounded curve like this separates a Euclidean plane into the outside and inside. It seems trivial, it seems easy to prove, to say, oh yeah, if I take a curve like that, it separates inside from outside. Turns out that some really smart mathematicians worked really hard and eventually proved it. The same mathematicians, Tarski in this case, were able to demonstrate that a Klein model does not, a sphere, imagine a hollow sphere. It separates the universe into the space inside of the sphere and the rest of the universe. So a sphere separates the universe into inside and outside. A cool thing is that a Klein model can be shown by the same methodology to not separate the universe into an inside and an outside. Is that there's something truly weird about a Klein model. It has no inside, it has no outside. A four-dimensional Klein model, one that actually is existent in 4 space. This is if I were to take a camera and take a picture of this object right here, and then I print it on a piece of paper, how many dimensions would the picture have? 1, 2, 3, 5, 7? 2-dimensional, exactly. It would have height and width, but there'd be no depth unless you were wearing those cool glasses. Yeah. But in other words, a normal photograph has 2 dimensions. So if I take a picture of this object, I'm taking a 3-dimensional object, right? An object that is 3-dimensional, and I'm showing you a 2-dimensional shadow. We're accustomed to this. We say, oh yeah, a picture, we don't even say it's a 2D shadow, it's a 2D representative, it's an image. A mathematician will say, oh, it's an embedding. We are taking something that exists in 3 space and moving it into 2 space as accurately as we can. In the same way, this, and the pieces of glass that I hope you're circulating and not dropping, this is a shadow of a 4-dimensional object in 3 space. So, unfortunately, in 3 space, we can't have self-intersection. Oh, I'm sorry, I didn't want to say this, but I gotta say it. It's so cool. Think about a string for a minute, right? So, I've got a string like this, right? So, if I have a 1-dimensional universe, in other words, a straight line, can I have a string in 1 space? Yeah, it'll be a straight line. It's a string that, can I bend it? No, I can't. Suppose I have a 2-dimensional universe, a flat land like the stage, right? Here's 2 space. Can I have a string embedded in flat land in 2 space? Yeah, sure. In fact, this almost does it right now. This, right? There's a string in 2 space. Can I tie a knot in a string that's embedded in 2 space?
You probably could.
Is it possible?
Sure.
No, of course you can't. Why can you not? Why can you not? Why won't it work? So here's a string. Here's a string. To tie a knot, I have something like this, right? There's a knot. Can I make that knot in a two-dimensional surface? No, why not?
No way.
He says it needs to be squished down. Yes, no? In other words, if I have a knot like this, it bumps up someplace. And I can't squash it down into the two space. I can't make, no matter how hard I try, it's just going to stay there. In two space, I can have strings and they can curve, as you point out, but I can't have a real, genuine overhand knot, a square knot, a granny knot. I can't have a knot because it sticks up like a pretzel. Okay, in three space, height, width, depth, our universe, can I have a knot? Prove it. Can I have a knot? What? Yeah. In other words, I can trace out that goes like this, right? And right? In other words, in three space, I have no problem whatsoever making a knot. The cool thing is, the wonderful thing is, this guy, Felix Klein, asked himself in four space, remember, height, width, depth, and something else, W? In three space, I can tie a knot because a string, right? I have a string. It doesn't, it stops. So I go like this, right? In four space, strings go right through one another. In other words, I go like this, and the string just goes right through itself. Can I tie a knot in four space? No. 130 years ago, Felix Klein pointed this out. What this is telling me is, hey, will DNA work in four space? No, it requires, will proteins properly fold in four space? No, they can't. You have a grossly different way of thinking about things. And Felix Klein realized this when he was researching very deep math. Today, string theory doesn't just apply to tying your shoes. String theory is at the real core of our understanding of the universe. And trying to understand how strings and superstrings work with one another, it's based entirely on the mathematics of topology. You serious? May I have it for a while? No? Okay. Similarly, in a Klein model, this self-intersection would not exist because the tube could go through this boundary without any self-intersection, just as a string goes through itself. In our four space, folding your arms like this wouldn't have much effect. Your arm would go right through like this. It's like, likewise, here, an ant walking along here would go right through this part of the manifold and come back over here. An ant walking along here would go right through there, continue onward. It'd be absolutely cool. It would be impossible to keep secrets because you could wander anywhere and walls would have a tough time stopping you. Happily, we don't live in that universe. People have seen this? Should I pass this back? Oh, crap. Oh, sorry. What? 9 minutes. So this means 9. Since time is a little bit tight here. I just thought I'd mention a few things. Like I assume everybody else here, I found myself doing laundry at the laundromat and over on Telegraph Avenue, and my jeans had holes in the knees. So walking along, I had, holes in my jeans, and they came out of the wash. Instead of looking like this, they came out of the wash looking like this. So I looked at this and I said, it was a part of my pants. I looked at it and said, hey, that's kind of weird. And I compared it to what I had sewn when I had sewn this thing together. I said, that's kind of strange because it ought to be possible to then turn this around and connect this into a Klein bottle, which I went ahead and got out my Singer sewing machine, and with the other pants leg, sewed the very end to the top, and this indeed is a hand-sewn Klein bottle made out of an old pair of dungarees. And you sort of roll your eyes and say, it doesn't look as cool as these glass ones that you're fooling around with, but to a mathematician, this is every bit as interesting as that is. The mathematicians are happy to write the equations and the representations. Again, when you drop it, run away. Okay, good. Having said that, I'll just mention that making these Klein bottles, visible, yes, no? A little bit, good, that's all I need. We make these over in the flatlands of Berkeley, over near San Pablo and Ashby, at Adams and Chittenden Glass, where these are mounted on an instrument on a tool called a glass lathe. And you can see a torch underneath here, and each of these bottles is heated and welded in 3 places, and it's a lot of hot glass. So over the past 20 years, we figured out how to make these relatively cheaply, so I make them for mathematicians. And, who remembers about this Mobius loop? We gave it a half twist. What would happen if we gave it a full twist? Would it still be a Mobius loop? No. What if we gave it 1.5 twists? Yeah, who says yes? Why do you say yes? Why is 1.5 twists just as good as 1/2 twist? How come? Quick, tell me. It goes back on itself. It would have 2 edges then, right? The third one gives... So, how about, suppose I gave it 17 half twists. Is it or is it not a Mobius loop? It is. How do you know? Okay, what if I give it 1,393 half twists? So what's the magic ingredient if it's an odd number? Well, likewise, I could do the same if I took something that had 3 half twists. If I took 2 Mobius loops and each has 3 half twists, then I sewed their edges together. Is this a real Klein bottle or a fake Klein bottle? It's a real one because I made it out of 2 Mobius loops, theory, that had 3 half twists. On the other hand, what would happen if I started with a similar thing and used 1 full twist? Is this a Klein bottle? In fact, you're correct. This is not a Klein bottle. This is topologically homeomorphic. Oh, what a great word, homeomorphic. This is homeomorphic to a torus, to an inner tube, to a tire. because instead of making it from 2 Mobius loops, I made it from 2 fake Mobius loops, each one of which has a full twist. Yeah. So, oh, I gotta be quiet. I'm about to, there's too many goodies here. I'd like to show you, may I show 3? Should I show this one? Look what it is. Check this out. No. Nothing up my sleeve. Yeah, I threw a spiral onto it just for fun. Take this. Pass around that. Finally, I'll just say my son who attends a different high school from here, whose name I will not mention, was reading a mathematics book called A Comprehensive Introduction to Differential Geometry. And in the beginning, it asked some cool questions. And one of the cool questions, it said, oh, look at this. There's a Klein bottle over here, and the mathematics of that, and oh, that's kind of cool. And then it said, oh, what's the relationship for this? And eventually it came across with, oh, look at this. Here's a real textbook in mathematics, and it asked, look, this is a hole in a hole in a hole. So my son, being a high school student, said, that looks weird. I wonder if you can make something like this. So we took this and, look, too bad you can't see it anymore, guys. Power off, yeah. So anyway, we looked at it, and I think he used AutoCAD to turn it into an AutoCAD diagram. And from that, we went over to the glass lathe and made now this is, okay, is this a Klein bottle? No, it isn't. No, this is unrelated to a Klein bottle. It's a hole through a hole in a hole. So, check this out. So, gentle. This took most of last summer to make. It's a hole, right? My fingers are outlining a hole that goes through a hole that is a hole, right? A hole through a hole in a hole. Very, very gentle with this stuff. So, what's going on here is there are surfaces. Oh, does everybody have to leave? Oh, there are surfaces that in mathematics you can worry your way through, and really smart people, mathematicians, love this stuff. Notice the whole time, for the past 45 minutes or an hour, you hardly heard me talk about numbers at all. You hardly heard me talk about equations. I maybe have mentioned the quadratic equation. The joy of mathematics, the wonderful part of math, is the beauty of figuring out, oh, I can take a piece of paper and turn it into something that has only one side. I can do it again with 3 twists, with 5 twists. I can cut it up with a scissors, and even though I've cut it with a scissors, and then look at the remnants. Remember this? Quick. Up here, fast. Everybody's trying to get out. They're waiting for you. Remember how this is cut? Step back this way. No, apart from one. Okay. Check this out. Check this out. Ignore this piece. This piece in the middle. Who's it who did the cutting? Right? She delicately, carefully, and expertly cut that big Mobius loop in a way that what was left over is what? A Mobius loop. So she could come up with the scissors again, go and get another Mobius loop with another weird thing over here dangling from it. The joy of mathematics, the beauty of mathematics, is utterly intriguing and addictive and terrific. One of the sad things that happens is we're forced, students, you guys are forced to take classes where you have to meet certain standards, like, oh, AP this and honors that, and you have to take this. So much of mathematics has been burdened by its applications. It's useful. Mathematics is perhaps the most useful of all the arts. The sadness of it is that so many people think, oh, I don't like it. To me, mathematics has as much beauty in it as anything that Shakespeare has written. And it touches me in a way that just, that it touches me in a way that makes me both excited and contemplative. So I hope, with good luck, the next time you're sitting there saying, I can't figure out what's the meaning of this. Simultaneous equations, what are they trying to tell me? Buried within that chapter in your math book, hidden amongst the equations, is a little message coming out to you, which most of the time is hidden. And the little message says, which time is this? Go ahead. 7 more minutes? 5 minutes? 5 minutes?
Maybe.
Okay, everybody who's got to leave, leave this moment now. If you've got to leave, leave now. Quick! Get out of here. I've got to take 5 more minutes. I'll tell them the secret. Get out fast! There'll be 5 minutes soaring right after they leave. Okay, they're out of here. Okay, I was an undergraduate. in 1971 at State University of New York at Buffalo. And I'm an undergrad, and there were riots going on campus. Oh, for those of you who are trying to steal those glass bottles on your way out, please don't. Please leave them with me. Thank you. Leave them with that guy there. I'll take them. Now, so I was an undergraduate, and there were riots going on campus. People were protesting some war or something like this. And as I'm walking along across campus, this guy, I'm hearing these riots, and people are throwing bricks, and there's cops and things like this, and I don't care, because I'm studying physics. I'm an undergrad studying physics, Landau, Lipschitz, statistical mechanics, thermodynamics. And I'm walking across campus, pile of books under my arms, because midterms are coming up tomorrow, and this cop comes up to me and says, you're a student. I said, no, I'm not a rioter. I'm just studying physics, studying math and physics. I'm doing science. And the guy has a rifle. And he looks at me and says, "You're a long-haired hippie that's the rioter." And he takes his gun, aims at it, he goes, boom! And he shoots a tear gas canister, the size of a Pepsi can, goes whoosh in front of me. I get a breath of fresh tear gas, and this cop is coming after me with a gun, and he wants to clunk me over the head. I'd say, "Good God, this is crazy, this is insane, what am I doing here?" And this cop's coming after me, and it's tear gas, and I'm shouting, "No, I'm studying physics, I'm studying quantum mechanics." And this guy's he's using words on me that my mother never uses. And so he chases me across campus. I run over to the administration building. There's this bell tower. He chases me in. It's 10 o'clock at night. And this guy's, I look around and say, "This is insane." I run to the front door. There's nobody around. This cop is chasing me up the flight of stairs, 2 flights of stairs. I get up the 3rd floor, and there's a door in the wall about 1 meter high, half a meter wide. I hear this cop chasing after me. I'm thinking, I'm dead meat. I look at the door looks at me. I climb in, I pull it closed, it latches, and I hear this cop outside swearing at me. And I'm saying, "This is lunacy. Where am I?" I look around, I'm inside a wooden tower. It's the bell tower. You know the Carillion Tower on campus at Cal? We had something like it, made of wood, 5 stories high. It was a clock tower. At the very top, there were clocks. Then there would be bells. So I'm in the middle of it, and the cop's there, and he's can't get in, and I'm stuck in there. So I look, there's this circular staircase going around. In the middle of the staircase, it's dark, and I see a pendulum. This pendulum's going tick, 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 tick. I'm saying, "Oh, I know what that is. It's a pendulum. It must be part of a clock." There's a pendulum clock, and I'm thinking physics. I'm thinking, "Oh yeah, if the length of the pendulum determines how fast it ticks, right? The square root of its length is proportional to its period time, with the coefficient of gravity tossed in." So I'm thinking about that, but why am I here? What am I doing here? This is insane. Why am I here? So I look and say, "This is crazy." So I start climbing up these stairs, and I get most of the way up. And coming up from this mechanical clock down at the bottom, there's a place up at the top where little dowel splits off 4 directions, north, south, east, and west. And there's clocks. I'm inside of the clock tower, and I can see the hands of the clock turning very slowly, but they're turning backwards because, I'm inside the clock tower. Make sense? So I see a clock there, and the hands, they're pointing to 10 o'clock, but it looks backwards, and they're going backwards. So I'm thinking, what does it take to make time go backwards? Sure, I'm doing physics, and I'm thinking, there are these things called Lorentz contractions and all sorts of cool physics of time travel, but I'm thinking about that, and I'm saying, why am I here? What am I doing here? What am I doing here? So I look around, and above me, there's this cupola up there. There's a wooden ladder. I climb up this wooden ladder, push open a door, a little hatchway door. I stick my head up, and this is the cupola above the clocks. There's bells in there. I climb up, I look out, and there's chicken wire over the windows to keep the pigeons out. It doesn't work. And I look out, I'm looking down from like 100 feet, 200 feet. I'm looking down and seeing policemen shooting tear gas at students. I'm seeing students throwing bricks at the police, and I'm saying, this is crazy, this is insane. Why am I here? Then I remembered what my high school English teacher, Mr. Lincoln, taught me. Guy said, when they make bells, when they cast these big bells, they always take an inscription. They write an inscription on the bell itself. So that, when the bell rings, people will not only hear the bong, but they'll hear everything else. Meanwhile, looking around, this is crazy. So I figured, you've heard these bells on top, bong, 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 you've heard them. So I said, I'll check it out as long as I'm up here. So I go over and there's this bell here. It looks like a Liberty Bell. It's this big. I take my jacket, I wipe off the pigeon dung from it, and there's There's an inscription on it. I'll be damned. There's an inscription on the bell, just like my English teacher said. So at this time I'll tell you the words inscribed upon the Hayes Hall Tower bells. All truth is one. In this light, may science and religion endeavor here for the steady evolution of mankind, from darkness to light, from narrowness to broad-mindedness, from prejudice to tolerance. It is the voice of life which calls us to come and learn. Thank you very much.